speaker is Svorad Stolc. Welcome.
That's correct.
And Svorad is going to talk about MotionCam-3D, the next chapter of 3D vision. Thank you. Go ahead.
So thank you very much for the intro. My name is Svorad Stolc. I am the CTO of the Sensors division at Photoneo. As the title says, I'm going to speak about our new MotionCam-3D. That is a camera that we believe is marking the next chapter of the 3D vision, not only for the vision-guided robotics, but also for many other applications. And we hope that the engineers will find a use for this technology, and we definitely are on a mission to help them to do that. For those who don't know the Photoneo, we are a company, an SME based in Bratislava, Slovakia, with worldwide operations. We grew in last 5 years from, let's say, a matter of a couple of tens to almost 200 employees. We are on a mission to provide robot vision as a company and intelligence to the robots, and currently we have about 3,000 solutions worldwide. For our sensors primarily, but not only that, we won in the past basically all the major awards. We are very proud of being the winner of the Vision Award 2018, which was the last Vision. And since then, we have experienced a huge recognition for our technology, and I'm really proud that Vision is the opportunity for us to present our MotionCam to the actual real people. It is almost 2 years since I stand in front of a proper audience and able to speak to the people, not sitting in front of their screens only. So what the MotionCam-3D actually is, we believe that it's an ultimate 3D camera for dynamic scenes, but I have to point out that it's not only for the dynamic scenes, it also works fine for the stationary scenes. So it's a method that combines, we say, quality or accuracy of the standard structured light technology with a speed of time of flight. Don't take me wrong, it's not that we would be using time of flight principle. It is based on a technology that we invented, and it's called parallel structured light, but it can deliver data rates that are compatible or equal to time-of-flight cameras. I would start with a fundamental maybe question. I know that many people are already enthusiastic and using 3D data, but the question is why the 3D data is actually good, why we are not happy with just 2D data. And I would answer this question with these two examples. 2D data can be very informative, but there are many cases where it can just be misleading, like the short video that is on the left side. If one looks just from a single perspective and the scene is not very cooperative, not very information-rich, one can come to a false conclusion that there is something three-dimensional. One needs another perspective to actually verify that and recognize that it's nothing else, just a planar drawing on a sheet of paper. On the other side, there is a 3D methods where one gets a very good idea about the 3D structure of a scene. In my presentation, I have an example of a cog from a bicycle, which is scanned from multiple perspectives, and it is done with our scanner, with our software solution called Foxy 3D Meshing. Doesn't matter. The point is that with 3D, one can interpret and get to a correct conclusion for a much larger variety of use cases, which means, for example, if I need to, I don't know, recognize the best grasping place for complex objects, or, for example, if I need to realize whether there is just a printed picture of a three-dimensional object on a packaging, this wouldn't be able to do with a standard 2D camera. With a 3D camera, there is no problem. You see that there is an area that is in a constant distance from my robot, and I know where to touch and how to grasp the object. From the principle point of view, 3D sensing techniques are basically divided into two major categories. One of them is a category of triangulation methods. For that, one needs a multiple perspective. Another approach that is widely used currently is a measuring of time. Regarding the triangulation, the principle is essentially very simple. One looks at the scene from multiple perspectives, which closes a triangle based on the angles and the size of the baseline. One can estimate how far the particular point is from the camera system. While with the measuring time, for example, time of flight cameras work in this manner using this principle. One sends an impulse of a light to the scene and measure the time the light travels across the scene and bounces back to the camera. If I have such a very fast stopwatch, I can basically count the distance very easily. Of course, in reality, there need to be certain tricks applied, but that's another story. From the principle of approaches of different methods, there are multiple, right? So there are passive systems that we believe that can do fast acquisition, that can deliver real-time data, that's good, but the accuracy and the actual sensitivity of the method, of the passive method, depend on the object texture, and if there is, for example, a perfect white wall in front of the passive system, the system cannot recognize how far the wall is. In contrast to that, we have active stereo systems or the structured light system or in the end parallel structured light system, where we actively send some light signals into the scene and then interpret those signals by the camera and later on by the software to know what's going on in the scene. So if, for example, there is a homogeneous area in front of the camera, it doesn't matter because I deliberately sent a light code into the scene. This light code is readable then in this homogeneous area. It's even better than if this is textured. And then I read it back, and then I get a good signal to noise or signal readout. The motion cam is the very last principle on the right side. That is called parallel structured light. That basically extends upon standard structured light approach, and I will explain what are the principles of those methods later on. So I will start with a structured light. Here is an example of a sequence a standard structured light sensor sees. This sequence of patterns is sent over to the scene by a pattern projector in parallel or at the same time, it's captured by a camera system, and then these light codes are interpreted to get to such nice 3D model. If the scene is stationary, if nothing is moving, structured light sensors are wonderful and they deliver very good quality data. But now, what if the scene is moving actually? What if there is an object that is not stationary, that falls down and bounces back and so on? During this train of patterns that are sent to the scene, one gets an inconsistent data obviously, and if I reinterpret this data in a normal way, in a standard way, then I get just the nonsense, as you can see on the right-hand side. So what one can do with it? One can attempt to just acquire it faster, like shorter exposure times, take a faster camera and just shorten the exposure time. Or one can attempt to do something in parallel, so do it in one shot or at the shortest possible time. And that is exactly where the Photoneo invention comes into play. We have invented something that is called parallel structured light. So basically this patterning thing is done not on the projector side by sending, over the time multiple patterns. Instead, the laser projector does just a very simple laser sweep across the scene, no patterning whatsoever. And the pattern construction is done in the proprietary CMOS sensor that we have developed, and now it is inside of our MotionCam-3D. So essentially, the role of the projector and the camera swaps. So we are no longer sending multiple patterns into the scene. We are sending just one pattern and then taking or doing something on the camera side so that we construct those patterns and can we can post-process that and in a normal way as we would do with a standard structured light data. Good. So here's an example of the same falling ball captured by a MotionCam-3D. The same patterns are being captured by the camera, but it is not. You see that all those patterns are constructed in the same time instance, so the ball doesn't manage to fall further down because it's a snapshot system. And then obviously, if you take this data, interpret this data, and get a final 3D measurement, you get a consistent readout, as you can see on the right side. Here an example of videos, two videos. One is taken by our MotionCam-3D, 20 frames per second. There is a fan rotating in front of the camera at high speed. And regardless of this high speed, you don't see any motion artifacts on the fan blades. On the other hand, there is a video taken by a competitor system and based on the time of flight principle. And you see I hope that you agree with me that the data quality is quite different, that the resolution, noise, and everything is just worse. Here, just briefly, there are some advantages and disadvantages of different methods. On one side, you see quality of the structured light, then the speed of the active stereo or time of flight, and with our parallel structured light MotionCam-3D, you get basically the best out of both worlds. Here, a summary of key features of our MotionCam. It is fast. I have hopefully convinced you about that. But it is also high resolved, so you can go up to 2 megapixels per frame with MotionCam-3D. It can work as a standard scanner, or it can work in the dynamic mode. You can switch between these two modes if you like, also in real time. It has very practical scanning ranges. We have different models, altogether 5 different models calibrated to various working distances and resolutions. It suffers from no motion blur. It is industry ready. We have IP65 rating, PoE connection, thermal calibration. It is plug and play, so you can just conveniently connect to it, and so on and so forth. Robust scanning, and it's patented. Speaking of the robustness of this method, it works very well because it's laser-based. It works very well with various diverse material types. It works well with shiny materials, not completely glossy or not completely mirror-like. Of course, mirrors are very hard to scan, but if it has reasonable scattering part, the reflection, we can still scan it very well. Dark materials work very well, like dark rubber, or you can imagine even a surface of a mobile phone one can scan from an appropriate angle. Semi-transparent objects work very well. Ceramic, glass, food, organic, and so on and so forth. So it's actually something you will realize pretty quickly if you put your hand on the scanner, on the camera. Then, obviously, if there is a robustness and speed, we support plenty of different applications, ranging from picking and placing in static, but also in motion. I will show an example. Hand-eye bin picking, for example, box dimensioning and counting. Everything which is moving on a conveyor belt makes no problem to MotionCam-3D, so you get an area scan, a snapshot in time, regardless of the motion of the object. Inline quality inspection, real-time handheld 3D modeling, e-commerce, order fulfillment, AI-driven applications are obviously one of the targets, etc., etc. So here I come to a part where I want to show you a couple of examples. These 3 are from, let's say, a traditional domain of vision-guided robotics. It's bin picking, depalletization, and singulation. All 3 of these could be, in principle, done with a standard scanner because the scene is not moving rapidly. There is nothing really moving. But The question is how fast you can do it. And with MotionCam-3D, you can scan basically all the time, or you wait just a small fraction of a second to get a scan. You don't need to wait for the scan to be finished. Here is maybe more interesting or illustrative example where MotionCam is, or what MotionCam is good for. There are, at the beginning of the conveyor belt, there are two MotionCams just scanning the envelopes as they come in, and the robot knows the shape, knows the best, or derives the best grasping point. There is a barcode reader that reads the address and everything, and the robot takes it and puts it into the right bin based on what's written on the envelope. Here, a funny application with box counting and dimensioning. So as the boxes are just going very quickly under the camera, we get a shape. We put together a rather overcomplete scan of the box, and from that we can derive the shape and obviously also the count. And then here it's very raw video of our demonstrator that we have, or one of the demonstrators we have here at the Vision Fair, where we show that, well, obviously if there is a scene that rotates under the camera, the quality is not like compromised by the motion. So yet another example how nice it works. And also you can see the 3 different resolutions of 3 different camera models that we have. That brings me to the end of my presentation. If you didn't visit our booth yet, please come over. It's Hall 10, booth C40. And if you have any questions, I'd be glad to answer them.
Thank you. So let us give you a hand. Thank you, Svorad. I don't see any questions, but I have one. Because I had to leave, maybe I missed it, but you said the moving objects. Up to which speed can you capture them?
Well, obviously it depends on the resolution, but for the large, the L model, it can go up to 40 meters per second.
40?
40 meters per second. And that obviously give a huge room for various applications. And yeah.
Definitely. Thank you.
Thank you.
So thank you once again, Svorad Stolc from Photoneo.
You're welcome.